All right. Hello, everyone. We're so glad to have you here today for the BioBuilder Idea Accelerator Showcase. This was cohort 7 of this school year, which is hard to believe for me after having seen so many great projects throughout the year. And I'm so excited to highlight a few schools today that we've been working with. So to start off, BioBuilder as a program is all about bringing tomorrow's science into today's classrooms and really letting students get hands-on with both the products and the ideas behind synthetic biology and biotechnology. And through this Idea Accelerator program, we're really excited about letting students do their own biodesign projects and engage with some of the cutting-edge technologies in synthetic biology by designing a new way that they would want to change the world using biotechnology.
So, our initial inspiration was a documentary that depicted the harsh lives of those who suffer from homelessness. Our proposal calls for a tree big enough to sustain human inhabitants. So, you're probably wondering how are we going to do this? So, first, we thought of incorporating genes from hollowed fruits such as bell peppers to help naturally hollow out our trees. We also wanted to incorporate chelated soil to help nurture our trees. So, in order to talk about our innovation and how we're going to make houses out of trees, we need to understand how a trunk hollows out to begin with.
Some of the tools we're using are the extraction of DNA. So we would need to extract DNA from bell peppers or whichever hollowed fruit we choose to continue into the tree. And we would need a PCR test to expand gene, and we need to use gel electrophoresis as well. Additionally, we would also need the injection tool to inject the pathogen into the tree and the fungi into the tree. We know that hollow structures are known to be less strong than those of smooth structures. Thus, we have decided to incorporate a chelated soil fertilizer, which will help supply the necessary nutrients to maintain our trees strong. Some questions we still have that need answering is how will the people living in our trees have access to toiletries? How will we incorporate electricity to the tree? And how will this affect the natural habitat for the animals? How will the Indian fungi affect the humans? And how will the Arena Karatova pathogen affect the humans?
Hello, my name is Joshua Flores, and with my team, Blooming Algae, formed by Chloe McLeod, Esther, Amari Wellington, and Jalen Jarrett, who sadly was not able to do testing, we have decided to synthetically amplify a strand of microalgae named Chlamydomonas to increase the production of the RuBisCo enzyme and support lipid formation, and in turn produce a higher quantity of biodiesel. Our goal is to create a more sustainable, environmentally friendly, stable source of biodiesel. Now I'd like to introduce Chloe McLeod, who will explain more of the process we've planned out.
Hello, my name is Boynton Beach, and I will be providing more information on our experiment. The chassis we decided to use is Chlamydomonas. We chose it because it is a well-documented species of algae that is known to be responsible for gene editing. We plan to increase the efficiency of photosynthesis by editing the RBCS gene to produce more of the RuBisCo enzyme, helping with the manufacturing of biodiesel. This will in turn improve the efficiency of photosynthesis and help increase lipid production and creation of biodiesel. This concludes our presentation, and I'd like to thank you for watching.
Today we're going to be presenting Don't Be Bitter, Be Better. Our introduction, our happier grapefruit. The healthiest citrus is also the bitterest. In order to increase the consumption of this fruit, we aim to reduce the bitterness. The focus of this project is to suppress the compound naringin by increasing enzymatic activity. This will be done to the grapefruit before being placed on the market so that consumers have the option of a healthy citrus with a less bitter taste.
The parts are enzyme CM12RHAT, and our fruit is Citrus X Paradisi.
Devices used were plasmid, promoter, ribosome binding site, and the terminator.
Using a CM1 gene to increase enzymatic activity will result in the suppression of the naringin compound. The input of the system will be the enzyme CM1. The output of the system will be a sweeter taste due to the reduction of the naringin compound.
The process is going to start off with it. We're going to start off with a grapefruit, and then we inject it with a plasmid. direct cells. Then while it's happening, the cells are gonna reproduce into new DNA. The outcome of it is gonna be less bitter taste.
With our experiment, we had the goal of creating a more naturally sweet chamomile. Commonly used for tea, chamomile or Matricaria chamomilla has been known for medicinal properties and usages. The input for the experiment would be sucrose synthase, an enzyme that promotes the production of fructose. The output of our experiment is the chamomile with the higher fructose levels than the norm. With the engineered chamomile, we plan to make tea that would not need any additional glucose supplements, allowing consumers to add fewer supplemental glucose sources.
Part levels, we do have a gene, enzyme, and hopeful output. Our gene would be sucrose synthase 2, and our enzyme would be sucrose synthase, hoping to promote sucrose production. For our device levels, we did not have enough source material to find a plasmid promoter, RBS, and terminator for our chamomile.
With the sucrose synthase gene, we plan to increase enzymatic activity of sucrose synthase. This enzyme will ultimately increase the production of fructose during photosynthesis. Testing this process will be accomplished by chemical glucose tests and taste testing groups. Thank you for listening.
Thank you.
Bye.
Thank you.